Hello, my name is Maite, and today I will be presenting the last oral presentation for English 2, which is about clay minerals. First, we will need a bit of an introduction. It is a complex subject with, we need to state some facts first. Rocks on Earth are mostly composed of silicate minerals. What does that mean? They are the most abundant. They are the most abundant type of mineral, constituting 90% of Earth's crust. What does that mean? Silicates are formed with this basic structure, which is a cation, meaning an atom with a positive charge, an silicate cation, surrounded by 4 oxygen anions, meaning an atom with negative charges. Because of the size of the relationship in size between silicon and oxygen, they can form this basic structure when solid, meaning a tetrahedron. I have 2 types of representation here for some clarity. For more information about why it forms this way, you can look in the Pauling laws. However, how they bond this different, imagine in a rock we have lots of this. How they bond between each other are the first classification between these types of minerals. We have nesosilicates, which are isolated, meaning this tetrahedron doesn't bond with any other tetrahedrons. It only bonds with other stuff, which doesn't matter right now. Sorosilicates, which bonds like in this oxygen, you have like another tetrahedron. Cyclosilicates, which bond in rings. Inosilicates are single or a double chain. I'll put some pictures later. Phyllosilicates, which bond in sheets, and tectosilicates, which are a 3D framework. In this case, we will, here we have nesosilicates, only 1, sorosilicates 2, cyclosilicates, they form in this way, and they can be represented 3D also. Single or double chained, and phyllosilicates, and of course tetrasilicates, which are all bonded basically. However, our part of interest today is on phyllosilicates, so we will focus on this group right now. They are silicon oxygen tetrahedrons form sheets and have a characteristic sheet appearance with very good cleavage, meaning, I think I've messed this up. In English it's not called cleavage, it's something else, sorry. But meaning they can they form this sort of appearance and can very easily be separated by these sheets. Meaning their atomic structure can also manifest on a macroscopic scale, which is pretty cool. However, other cations, other atoms with positive charge, can replace the silicon inside the tetrahedron, the most common being aluminium. If you saw on the first slide, you can see that silicon has a 4+ charge. However, the aluminium only has a 3+ charge. That creates a vacancy in charge the structure is not stable, and will require other ions to reach electric neutrality. Well, moving further, we will focus specifically on aluminosilicates, which are, of course, structures or minerals that both contain structures with aluminum and oxygen and the silicon tetrahedron that I previously mentioned. The aluminium is a bit bigger in size than silicon, so they will be able to bond with more oxygens. So they won't form a tetrahedron but a octahedron. So when they lay in sheets like this, they are actually like tilted down in some way and form this structure. This the blue ones are aluminium, this big one is hydrogen, and this one is oxygen. The opposite, sorry. This is oxygen and this is hydrogen. That is that is as well. So I have to state for before that there are many types of minerals, types of silicates that can be aluminosilicates, ferrosilicates, but also tectosilicates can be aluminosilicates in some cases, like feldspar, clay minerals or micas, for example. Well, moving further, now that we have made the introduction, clays. What are we talking when we talk about clays? One would imagine the thing that we use to make pots or other china, But in a more specific term, we can talk about a lot of things. We can talk about the size of the grain. The sediment in itself can be many sizes. Like we have sand, but we can go smaller, like in the case of clay. As we can see, we have pebbles, granules, very coarse sand, medium sand, fine sand, very fine sand, and silt or clay, which is stated as a maximum of 0.063 millimeters. We can also be talking about clay minerals, which are the minerals that most commonly form these types of sediments and have some specific characteristics that make them so useful in the industry. Well, moving to a definition of clay minerals, they are hydrous aluminium phyllosilicates, meaning hydrous phyllosilicates, but they are also in the aluminosilicates. It is it is a mouthful, sorry. So the layers of the tetrahedrons bond with the aluminium octahedrons. There are also like a wider variety of these kinds of bondings. For example, we have the one clays, which are one sheet of octahedrons, aluminium octahedrons, and one sheet of silicon tetrahedrons. Now you can see the oxygen in this one is bonding with the oxygen in this one. there isn't always a correlation. As you can see here, this one isn't bonding. Oh yeah, it is. Sorry, this oxygen is not bonding because of the way they form. It doesn't matter right now. And you can also have, as we mentioned earlier, the in this case hydrogen cations that make the structure electrically neutral. We can have also the 2,1 clays. Well, sorry, this example uses kaolinite, sorry, kaolinita, which is a very common clay mineral. We have the 2,1 clays. We'll go for in the non-swelling part later, which are the octahedrons of aluminium, bonded on the bottom and on the top with silicon tetrahedrons. There are also some cations present. Sorry, I completely forgot to mention why they are hydrous. These types of structures can have water bonded inside of the layer, giving them properties. It doesn't mean they can hold water in itself. It's more like it's bonded in the structure. So we will go there later. So going back, going now through this, we have one sheet and two sheets, like a sort of sandwich. Then we have this in this case we use Elite as representative of the group. And then we have the 2,1 swelling clays, which are which have interlayer water. In this case, it's not necessarily bonded to the structure. It is just there, but well, of course, in a molecular level, you can't actually see the water, but it can make it expand. So we have this sandwich here, but also in between these sandwiches, which I imagine in a very small scale to be able to see them, you have to have a lot of sandwiches. So we have water that makes the clay swell. This type of clay is found here in Uruguay, and poses a relatively big threat to the structure of some buildings. For example, the Peñarol Stadium, which has shown cracks, if I'm not mistaken. And then we have chlorides, which have two sandwiches, and in between we have another interlayer of aluminium, but some aluminiums are maybe actually they are magnesium and ferrum, sorry, and iron. Well, how do they come to be? Well, clay minerals are a stable byproduct of the decomposition of other aluminicics. This is a lot to take on firsthand. But what you have to know is, secondary minerals or byproduct is something that basically a mineral goes through a process. It may be weathering or magmatism or metamorphism that makes it change to another type of mineral. It usually, of course, has the same components, the same elements, of course, because it is formed with the help of the first mineral. We will be focusing, although clay minerals can be formed in many ways, we will focus today on the weathering part. Okay, so we will talk about a bit about the geological cycle, which is you first have a magma, of course. Very hot rock that has melted subsurface and can crystallize subsurface or come up as lava, Then you have the igneous rock that has formed from the crystallization of that magma. That igneous rock can go through weathering and erosion. That meaning, when it formed in those types of environments, the rock was at a much higher temperature and a much higher pressure underneath. When it comes up due to many reasons, it is not stable with the environment. Sorry. Wait a second. Well, continuing. Sorry, I had to shut down that. Coming to the surface, which has a much lower pressure and a much lower temperature, the rocks are not in equilibrium with the environment that formed them. So they have to go through processes which are weathering and erosion in this case. Chemically unstable or relatively cool, works and oxidizing. Of course, water also comes into place into part in this case. It is a big part of the we have chemical, physical and biological weathering. We will in this case of course be focusing on the chemical weathering, which has a lot of types. It is encompasses many different processes that can chemically alter the rock, forming more stable products. In this case, for example, clays. Water is a crucial part of this process, and it is responsible for most of these reactions. It percolates through the rock, through cracks, reacting and altering it. These reactions convert some of the original primary minerals, as I talked earlier, into the rock to secondary minerals, which are formed by the same compounds. They can also remove other substances, like for example dissolving them, and leaving the most stable minerals, which were maybe formed under lower pressure and temperature, so they are a bit more stable in the surface. So they can be chemically unchanged and alcohol resisted. Here we have, for example, as we saw earlier, clays form part of the secondary minerals in this reaction. We will be going through one only process because it's getting a bit too long. But we have here, for example, albite, which is a type of feldspar that has sodium in it. Each in turn by a process called hydrolysis, which is stated here: solution, hydrolysis, oxidation, carbonation, spheroidal weathering, and hydration. Hydrolysis is basically the properties of water can tear apart the structure of minerals or other other things in general, but in this case we'll focus on minerals. We have the albite, as I said just now, which is a type of feldspar. As I said earlier, feldspars in general are aluminium silicates and also clay minerals. So the secondary mineral in this case will be expected to have that aluminium. Especially aluminium is an element that doesn't have a lot of mobility. It doesn't go. It doesn't dissolve very easily and doesn't really move from the rock unless it's very extreme conditions. So we will be expecting to have the kaolinite, meaning the one clay in this case, which has also aluminium. And this is the solute, which is a bit of silicate with some water, meaning doesn't matter, some sodium ions, which in this case are very soluble, as we know, for example, table salt. As water percolates and takes away all these solubles, it leaves behind this white mess, which is formed, and it is the kaolinite in this case. Well, thank you. In this presentation I used information from the 2 courses I'm taking in this semester, which are mineralogy. In this part I explained all the structure, and the formation processes I took from geochemistry. So this way I took something in common from both of them. Well, thank you for your time, and thank you.